Right now, more than 12 billion miles from Earth, a nearly 50-year-old spacecraft is picking up a signal that shouldn't technically be possible to hear. It's not a transmission from another civilization. It's something stranger in its own way. A faint, steady tone rippling through the empty space between the stars, and NASA scientists only recently figured out how to actually listen for it. This is the story of the frequency Voyager 2 picked up after leaving our solar system entirely, what that tone is actually made of, and why detecting it at all required an instrument that almost didn't survive long enough to make the discovery. Stick around, because the physics behind this faint, constant hum is honestly stranger than fiction. And if you want to catch every new update as these two incredible spacecraft keep listening to the space around them, go ahead and hit follow before we get into it. To understand what Voyager 2 actually detected, you first need to understand where it is and how remarkable it is that it's still working at all. Voyager 2 launched all the way back in August of 1977, alongside its twin, Voyager 1, on a mission originally planned to last just a few years, flying past Jupiter and Saturn before, in Voyager 2's case, continuing on to a rare and historic tour of Uranus and Neptune as well. Once that planetary tour wrapped up in 1989, the spacecraft kept going, drifting steadily outward, and on November 5th, 2018, it crossed a boundary that only one other human-made object had ever crossed before. It left the heliosphere, the vast bubble of charged particles and magnetic fields blown outward by our own sun, and entered true interstellar space, the region between stars where the sun's influence essentially fades to nothing and material from elsewhere in the galaxy takes over. Confirming that crossing wasn't as simple as it might sound, because there's no visible line marking the edge of the solar system, no sign that says you have now left the building. Scientists had to rely on Voyager 2's instruments detecting specific physical changes in its surroundings, and this is where the frequency detection actually comes in. Voyager 2 carries something Voyager 1, unfortunately lost decades ago, a fully functioning plasma science instrument, capable of directly measuring the density, temperature, and speed of the charged particles surrounding the spacecraft in real time. Voyager 1's equivalent instrument failed back in 1980. Which meant that when Voyager 1 crossed into interstellar space in 2012, scientists had to wait for an indirect signal, a burst of energy from a passing solar storm to infer what the plasma density actually looked like. Voyager 2 didn't have to wait for a lucky break. It could measure its environment directly, continuously, the moment it crossed over. And what it found lined up with something researchers had specifically been listening for, a distinctive plasma wave signature, essentially a tone produced by electrons oscillating within the surrounding gas. Here's how that actually works. Space isn't a perfect vacuum, not even in the supposedly empty stretches between stars. It's filled with an extremely thin, diffuse soup of charged particles called plasma. When that plasma gets disturbed, whether by a shock wave from a distant solar eruption or simply by its own natural thermal jitter, the electrons within it oscillate back and forth at a specific frequency, one that depends directly on how densely packed those particles are. Denser plasma produces a higher frequency oscillation. Sparser plasma produces a lower one. It's essentially the same physical principle behind an instrument being tuned to a particular pitch, except instead of sound waves moving through air, these are electron oscillations moving through ionized gas. And instead of a musician tuning it, the density of interstellar space itself sets the note. When Voyager 1 made its own crossing back in 2012, NASA scientist Don Gurnett, who led the plasma wave investigation on both spacecraft, described listening to those recorded oscillations almost like a tuning fork test. While Voyager 1 was still inside the heliosphere, its plasma wave instrument recorded low tones hovering around 300 Hz, typical of the relatively sparse solar wind. The moment it crossed into interstellar space, that tone jumped dramatically higher into a range between 2 and 3 kHz, a clear, unmistakable signature of the much denser plasma that fills true interstellar space. Gurnett called that shift the transition music, and it was at the time the clearest evidence NASA had that Voyager 1 had genuinely left the solar system behind. Voyager 2 gave scientists a second, independent version of that exact same story, this time measured directly rather than inferred from a lucky solar event. Researchers led by physicists at the University of Iowa confirmed Voyager 2's crossing by identifying a clear, definitive jump in plasma density recorded by its working plasma wave instrument right at the moment of the boundary crossing, published in a study in November of 2019. Because Voyager 2's instrument could keep measuring continuously afterward, rather than waiting for another solar storm to happen to pass by, it gave scientists something Voyager 1 alone couldn't offer, an ongoing steady stream of direct plasma readings from two separate points in interstellar space, gathered years apart along two completely different trajectories out of the solar system. That combination turned out to be scientifically invaluable. A follow-up study led by physicist William Kurth used Voyager 2's continuing measurements to map out something called a radial density gradient in what's known as the very local interstellar medium, essentially tracking exactly how the density of interstellar plasma changes as you move farther and farther away from the heliopause. Having two spacecraft crossing into interstellar space 6 years apart at different locations gave researchers something close to a three-dimensional picture of how this material is actually distributed just outside our solar system's boundary, rather than a single, isolated data point. Then, in 2021, researchers analyzing years of accumulated Voyager 1 data uncovered something even stranger layered on top of these earlier, more dramatic frequency spikes. Buried in the background, beneath the occasional loud bursts triggered by solar storms, was a persistent, extremely faint, and remarkably steady hum, a narrow band signal that had apparently been quietly present since 2017 and had simply gone unnoticed until Cornell astronomer Stella Koch-Ocker specifically went looking for it. She described the discovery in strikingly simple terms, noting that the signal was very faint and monotone, confined to an unusually narrow slice of the frequency spectrum, essentially the persistent background drone of interstellar gas itself, rather than the sharp, temporary spike caused by a passing solar event. Unlike the earlier detections, which depended entirely on the lucky timing of a solar eruption reaching the spacecraft, this continuous hum meant scientists no longer needed to wait around for a fortuitous burst of solar activity just to get a fresh reading of the interstellar plasma density surrounding the spacecraft. Scientists still aren't entirely certain what mechanism produces that persistent background tone. The leading theories point towards some combination of thermally excited plasma oscillations and a phenomenon called quasi-thermal noise, essentially the natural low-level electrostatic jitter produced by charged particles randomly bumping and vibrating due to their own inherent thermal energy, even without any dramatic external trigger, like a solar storm setting them off. It's less like a deliberate broadcast and more like the ambient background. Noise of space itself, the collective murmur of countless charged particles gently vibrating in an environment so close to a true vacuum that even this faint signal becomes measurable and meaningful. What makes all of this genuinely valuable to scientists isn't the poetic idea of a spacecraft picking up the sound of the universe, as compelling as that framing is. It's the practical scientific value packed into that signal. The frequency of these plasma oscillations translates directly into a precise measurement of electron density in the surrounding interstellar medium, and tracking how that density changes, both over time and across different locations, tells researchers an enormous amount about the physical structure of the material sitting just outside our solar system's boundary. It helps map out turbulence in the interstellar medium, reveals how the boundary of the heliosphere interacts with the material beyond it, and provides an ongoing, evolving picture of an environment that, until Voyager physically got there, existed only in theoretical models built from indirect observations made through telescopes back here on Earth. There's something worth sitting with in the fact that Voyager 2's ability to detect any of this at all came down to a single piece of hardware, its plasma science instrument, quietly surviving nearly 4 decades of continuous operation in one of the harshest environments any spacecraft has ever traveled through. Voyager 1's equivalent instrument failed decades ago, permanently limiting what the spacecraft alone could measure directly. Voyager 2 got luckier, and that stroke of engineering fortune turned it into an irreplaceable second set of eyes and ears, giving scientists direct, continuous access to a region of space that would otherwise remain almost entirely invisible. Both spacecraft are still out there right now, still listening, even as engineers back on Earth continue making difficult decisions about which instruments to keep running as each spacecraft's nuclear power source steadily decays year after year. NASA officials have suggested both missions could realistically continue for another few years before power finally drops too low to keep any instruments functioning at all. Every additional month either spacecraft keeps transmitting is another chance to refine this ongoing map of the plasma frequency surrounding our solar system, deepening a picture of interstellar space that, until less than a decade ago, existed almost entirely in theory. So somewhere out past the edge of the solar system, Voyager 2 continues drifting through true interstellar space, its plasma instrument still quietly tuned to the faint electrical hum of the gas surrounding it, translating that hum into a steady stream of density measurements scientists are still using to understand the structure of the space between the stars. It's not a message from anyone. It's simply the sound, in a very real physical sense, of the universe's own background. Plasma vibrating at frequencies of 50-year-old spacecraft happens to still be capable of hearing and translating that faint vibration into some of the most valuable data humanity has ever collected about the true edge of our solar system. If a story like this, an aging spacecraft literally tuning into the electrical hum of interstellar space itself, is the kind of thing that genuinely fascinates you, go ahead and subscribe. Drop a comment letting me know what you think this faint signal might reveal next, and stick around because there's a real chance these two remarkable spacecraft are still picking up more than anyone has managed to notice yet.